All right, let's walk our way through an AP-style free response problem that involves buffers. So lactic acid is a monoprotic acid that dissociates in aqueous solution represented by the equation above. Lactic acid is 1.66% dissociated at 298 Kelvin in 0.5 molar lactic acid. So we're going to assume throughout the problem that the temperature remains constant at 298 Kelvin. So let's address parts A and B first. First, write the expression for the acid dissociation constant Ka for lactic acid and calculate its value. And part B, calculate the pH of 0.5 molar lactic acid. Okay. So part A, write the expression for the acid dissociation constant Ka for lactic acid and calculate its value. Well, here's the Ka expression. Concentration of H+, concentration of lactate, that's the concentration of the products, divided by the concentration of the lactic acid or the reactant. Now, we're given the original concentration, 0.5 molar, of the acid, and we need to find the concentration of H+ and lactate. We can do that because we're told that the acid is 1.66% dissociated. So we know how much of the acid has dissociated and therefore how much of it has become product. So we can say that 0.5 molar acid, the original amount of the acid, times the percent dissociation, 0.0166, is equal to 0.80083 molar. So that is how much of the acid has dissociated. So we can make an equilibrium ice table and say that we start out with 0.5 molar lactic acid. We dissociate some amount, and we're told that that amount, X, is 1.66% of the original amount, which is 0.0083 molar. And given the stoichiometry here, that means that both the H+ and the lactate amount increase by that X. So we have our amounts of all of our reactants and products at equilibrium that we can now substitute into our Ka expression. So we have the concentration of the products, which is the same, 0.0083 times 0.0083, over the concentration of the reactant, 0.5 minus 0.0083. And of course, ordinarily, when we don't know what X is, we assume that that X is very small here. Remember, that's when the percent dissociation is less than 5%. But since we know the amount here, we may as well use it. When we do that, we get a Ka of 1.4 times 10 to the minus fourth. Okay, so that's Ka for lactic acid. Now, part B asks us to find the pH of this 0.5 molar solution. And remember that pH is related to the H+ concentration, which here H+ is defined as X or 0.0083 molar. So we find the pH as the minus log of the hydrogen ion concentration, or the minus log of 0.0083, gives us a pH of 2.08. So that's parts A and B. Let's go ahead to part C now. In part C, we're going to make a buffered solution and calculate the pH of that buffer. So it says, calculate the pH of a solution formed by dissolving 0.045 moles of sodium lactate in 250 milliliters of 0.5 molar lactic acid, assuming that the change in volume is negligible. So this is a buffered solution where we have lactic acid and a salt containing the conjugate base lactate. So we're finding the pH of the buffer, and I'm going to do that using the Henderson Hasselbach equation. So the first thing I'm going to do is find what is the concentration of that sodium lactate. So I know that I have 0.045 moles, in 250 milliliters. So 0.045 moles in 0.250 liters gives me an initial concentration of sodium lactate equal to 0.18 molar. So I have this initial amount of acid and base. And so, of course, once I add the sodium lactate to the 0.5 molar lactic acid, the equilibrium is going to shift, right? So what's going to happen? Well, I'm going to decrease my lactic acid concentration, increase both my H plus and my lactate concentration by an amount X. And I can find my new concentrations at equilibrium. So for the lactic acid, 0.5 minus X, for the hydrogen ion plus X, and for the lactate, 0.18 plus X. I can sub all of that into my original Ka expression from part A, keeping in mind here now that we'll assume that X is much, much less than 0.18 or 0.50, so that we can assume it's 0 here and here to calculate X. And X, of course, is the concentration of the hydrogen ion, again shown here. So we could take the negative log of that X to get a pH of 3.41, or as I mentioned before, use the Henderson-Hasselbach equation to say that the pH is the pKa, the minus log of the Ka, calculated in part A, plus the log of the base 0.18 over the acid 0.50 concentrations. And we get the same pH either way, so whichever way you're most comfortable, the pH of this buffered solution is 3.41. Okay, now in part D, we're going to add some strong acid and calculate the change in pH of the buffered solution given the addition of a strong acid. So the problem says a 100 milliliter sample of HCl is added to 100 milliliters of the 0.5 molar lactic acid. Calculate the concentration of the lactate ion in the resulting solution. Okay. All right, so first things first, I have to find my new concentration of lactate, okay, because I changed the volume. So I started with a 100 milliliter sample of lactic acid, and I'm adding an additional 100 milliliters to the solution, okay? So we can say, of course, M1V1 equals M2V2, since it's a monoprotic acid, to find the concentration after the new volume is added. And so we get that the new concentration is 0.25 molar lactic acid. Okay. Do the same thing with the HCl to find the volume after the two are combined. Again, M1V1 equals M2V2 to find the concentration after the addition or mixing of the two 100 milliliter solutions. So I have 0.05 molar HCl. And then let's take a look at what's happening here. So we have 0.25 molar lactic acid and 0.05 molar hydrogen ion from the HCl. Our reactant will decrease by some concentration X, and each of our products will increase by some concentration X. So that we have 0.25 minus X, 0.05 plus X, and X at equilibrium as our equilibrium concentrations. So we can use our Ka expression and assume that the concentration, of course, is much, much less than 0.05 or 0.25. And so we can say that Ka is equal to the concentration of the products, 0.05 times X, over the concentration of the reactant, 0.25. And we get that X is 7.0 times 10 to the minus 4. And that's what we're looking for, the concentration of the lactate ion in the resulting solution. So we're just being asked here to solve for X. Okay, so there's a full-length AP buffer free response example given lactic acid and sodium lactate.